Okay, I guess this is the last presentation of the day, and I'm going to talk about some IP. This is one of the things I've been working and involved in a few years now. How many of you know about some IP? So now, okay, awesome, great. I want to learn more what's happening, so this is good time. This is a large presentation, but I don't think I'm going to go through everything, considering we are already at 4:30 p.m. And even there is a larger presentation on this with probably 90 slides on that, so I had to shrink it for a 30-minute presentation today. So I'll go through this agenda basically, talk about basics of service-oriented architecture and why some IP, basic messaging and protocol description, how Autosar describes it, classic Autosar, and use of ARXML for some IP description. I'll talk a little bit more on service discovery compared to other parts of some IP. And then there is a framework which we worked upon for testing some IP stack of your own, or using a available free stack and profiling your application with some IP. And then we'll have some concluding remarks. Okay, service-oriented architecture. This is, we hear so many times, and many OEMs are going towards this architecture for various reasons. And what is a service? To begin with, service is really a self-contained unit or functionality. It's a piece of software. It's an independent piece of software with very clear defined interfaces. And this piece of software provides certain functionality which is accessed by some other system, some other node on the network. There are consumers and producers of a software service. So a producer produces the service, and the consumer is going to consume the service. There is a mechanism called RPC, where one consumer can request or RPC certain functions from a provider. The key element, which I think is most prominent from my perspective, is service discovery part or message broking part. You know, this service broker or service discovery, this term is very popular. But in case of automotive, it's more a service discovery as a term used here. The key thing about some IP or service discovery is the runtime communication path. This means if a consumer needs certain information or want to invoke a specific method in a remote node, it can establish a runtime communication path. This means it can say, okay, this is the time I want to talk to you, and this is the time I want to stop talking to you. So these runtime communication paths have great implications because it can conserve bandwidth on the critical legs of the network. The other key thing is there could be parallelization between the same client and server. So there could be multiple transactions going on between the client and server. So those all sessions could be parallel running with each other. Client-server architecture, consumer-provider behavior, and publish-subscribe are typical transaction models in some IP or service-oriented architecture. So a little bit history on some IP. BMW in 2011 actually first time talked about it. They have the real credit of bringing this middleware into automotive. Some IP is a type of service-oriented protocol. There are other protocols, but some IP is one which is very much customized by Autosar for automotive. So a lot of credit goes to Autosar Consortium for specifying some IP for automotive. After BMW discovered it or created it, Autosar specified it. The key element about service-oriented architecture is complex data communication. For example, we have, if a point cloud information, a radar detects a certain image, there is a whole array or a structure of data to be sent to whoever needs that information. And this kind of complex data communication paths or communication can happen really truly only in a service-oriented architecture. Signal-oriented communication is not that capable and efficient for such kind of communication. Key for some IP is an application layer high up in the Ethernet stack. It is the layer, seventh layer on top, along with DOI for HCP or Ethernet and things like that. So the whole crux of some IP is IP and basically Ethernet. The good thing about SOMIP, it's a middleware. Essentially, it is independent of the underlying hardware. This means it doesn't know what hardware it is running on, or basically it's being such a high layer, it doesn't care. So that has a lot of advantages, as we'll see further. Autosar very well specifies some IP in the terms of PDUs, ports, and data types of exchanging of data types. It describes the serialization technique. It describes everything you need to implement, some IP and some IP service discovery. I have this very simplified picture which shows what some IP is. There is a consumer ECU which essentially subscribes to a service, and I described service. It's a piece of independently running software. For now, that probably is enough for us to go further into this presentation. So it subscribes to a service, and it can receive event notification. It can invoke a method into the server. It can get field notification, and it can have request response communication. It can request something, and provider is will respond to that request. On the provider side, it offers the service and provides endpoint details where a provider can contact the consumer can communicate or contact provider for that service. And the service has fields and events. I'll describe that more, and it has methods. Fields have getter, setters, and notifiers. Again, I'm going to describe them more later, but these terms are extremely important, and these are the key terms for some IP. You can see a simple switched network here, where there is network endpoint ECU A, which is a consumer, and network endpoint ECU B, which is a provider. There is an IP address 192.168.10.100. That's the endpoint address here, and here it is 101. Then there is a port called 30490. Actually, there is a mistake here. It should be 30490. 499 is incorrect. It should be 30490. It's a typo mistake from me. That's a service discovery port. Service discovery port is 30490. Any transactions happening on that port are service discovery transactions. And that port is common across all endpoints. So all endpoints have multicast messaging going on 30490, which is the service discovery port. After that, port 30501 onwards are ephemeral ports for the application to reside. So that's where the applications reside, which has the service implementation, for example. Classical signal-based communication, or the CAN, it is inefficient for larger data transactions and also the dynamic data. I mean, once like if there is for example, again, taking the example of radar data, not every time there is a detection. And this means those endpoints on those IP addresses and port are communicating, but not every time they're sending the data. This means there is dynamics in the data. It's not like static CAN-based classical communication, which we know very well. Message going at 10 milliseconds forever goes at 10 milliseconds. Take it or leave it. That's not the case. Payload is fixed 8 bytes or 64 bytes. It goes, most of the signal-based communication is like that. But some IP is service-based communication is a lot more than that. There is dynamic payload transactions possible, which is extremely important. And also, because of the notification on events and field notifiers, it is possible to just subscribe to that part and get notified of the useful data only. So these are all the reasons why we have service-oriented architecture, adopted by many OEMs. And all the problems associated with statically defined interfaces and static architecture and the limitations of the static architecture are overcome by service-oriented architecture. And this allows, in fact, the vehicle compute ECUs becoming more capable after production, which is the key here, because we could update the whole network or all the ECUs with an OTA update and provide capability of new service consumption or provision inside the network in the same vehicle. So post-production, you could add value to the vehicle. And that is one of the biggest advantages of service-oriented architecture. The key thing is the endpoints do not need to reside in the vehicle. You could have endpoint sitting on the cloud, and a TCU kind of horizontal machine can communicate with the cloud endpoint to consume certain service at runtime. This is a simple architecture I made, simple example to actually talk about what service-oriented architecture is. I'm not going to describe everything out of this, but this slide, of course, is available. I just designed a simple switch network with 4 ECUs talking on a Ethernet communication, 1000 base T1 or 100 base T1. That doesn't matter because we are at application layer. And there are 4 ECUs, ECU 1, 2, 3, and 4. This is head unit ECU. This is vehicle control, for example. This is front camera. This is short range radar. And so you can see the way this is, you describe such a network with service oriented behavior is you see what services a specific endpoint provides. In this case, it provides audio control. In this case, it provides obstacle avoidance, for example. In this case, it provides object recognition, and here it is park assist info. But this ECU also consumes object recognition service and also consumes park assist info, which are provided by these 2 ECUs respectively. That is how a basic architecture view is. There are consumers and providers of the service, and each of these service have either events or methods or both. So there will be events, there will be fields, and there will be methods to like getter setter methods or notifier methods provided by each of these services. So this is how basic service oriented architecture can be described as. Again, these are some of the terms which I wanted to kind of make you aware that working on SOA or some IP, these are the terms one should be aware of what they are. We're not going to read through. I'm not going to read through all of them. They are specified in Autosar specification. Feel free to read from there. If you have questions, I done a lot of research in some IP. I can help answer those questions too. But essentially, there is a method. Method is basically a subroutine call, a function call based on RPC. So I can call into a remote node and invoke a certain method. Similarly, there is field. Field is typically your signal kind of information, and it has a value which I can either get or set. For example, I can request a audio control unit to increase the volume. So I can go and say set volume. So I can invoke a method, a set method. And before that, I can say get method, and it says volume is level 3. I want to put volume 4, so I can use the set method to set the volume 4. Service I described is, so service is a combination of method and events and fields. And basically, it's a piece of software essentially, and it has a very well-defined interface. So anybody who wants to consume the service, communicates to the service interface. This is a very simplistic, again, communication pattern. It's a publish subscribe kind of model, and I'm just gonna quickly flow through this. This is a client or consumer of the service, or basically subscriber of the service. During the some IP service discovery phase, it's gonna send out a message saying find service. This means this client is looking for a service. And in this case, if you take a tool like vehicle spy, it's going to show you the details of that in the message parser. In the message view, it will show you find service has been sent out, and the request for what service it is looking for is hex 1234 for example, in our case. And it's going to be sent to a multicast address where each endpoint can actually receive it and respond to it. Then the server can send a message out saying, okay, it does offer that service ID 1234. And with that, it will also announce what endpoints that service is available at. So in this case, the service is available at endpoint 192.168.10.100, and protocol to be used for this communication is UDP, and the port is 305509. This is the server announcing the availability of that service at that endpoint. As soon as that is on the bus, the client will say, okay, I want to subscribe it. So here it is aware what this service content is. And it's going to say, okay, I see that you offer that service. I'm going to subscribe to your event group in this service. And it's going to say, I want to subscribe to event group. So it's going to send a service discovery message, which is subscribe event group type. It's going to say service ID is 1234, and it's going to provide the event group ID, which is in our case 4465. And it is also going to announce its endpoint where it's going to consume the event group or event group related information. And the port, so it has the IP address. Protocol is going to use is UDP, and then it's going to announce its port. Once that happens, the server is going to say, okay, I'm gonna accept your request to subscribe to this event group. It's gonna send an ACK message out. And once that happens, in the server side, there is entry made for this client with its port information. And then you can have a UDP-based messaging starting to go on the bus with the destination IP address and port as this from the server side. This means now, whenever certain event happens, this will be the source, this will be the destination, then you have the source port, you have the destination port, and then you send out the data which it subscribed to. So this way, anytime now, this is a very simplistic mechanism, but there are a lot of things around it, and there are different messaging type also. We'll see some of them today. This is very quick 3 or 4 slides I have. There is a lot more details to this, but in Autosar is the only way right now I know of where some IP is described for automotive use case. And Autosar describes 3 primary components: socket adapter layer, service discovery layer, and some IP serializer or transformer. And they're described in, you'll have to parse through all Autosar documentation in different releases and see some of them will be in the classic platform and some of will be in the adaptive platform. What I am describing is only Autosar classic based some IP right now, because the protocol engine itself is same, but the implications are different, or the way adaptive Autosar talks about it is really different. But the protocol itself is same. So I'm talking the Autosar classic perspective only. Socket adapter layer essentially in concept marries PDUs to the socket. So that is really where this is all I want to communicate today is it really talks, it links the PDUs to a socket or an IP address and port, and this is all described in Autosar. Essentially, you have a socket connection which has description of what PDUs are on that socket. And then such socket connections are used in socket connection bundles, and you can see all of that in ARXML file. So if you load ARXML file in a vSpy-X or vSpy-3, you'll see all the socket connections. This is a good view of how the socket adapter layers is used. It is used for multiple entities. One of them is service discovery, and this is how the Autosar describes the use of socket adapter for the application layers usage. Just quickly to talk about what service discovery does. What are the functions of service discovery layer? It describes basically what services are offered or consumed. It describes the instance of the service. Service is only valid if there is an instance available. It also describes event group IDs, and it has multiple mechanisms where it can describe multiple options in the initial communication messages. And it can describe there are various different options are possible. I'm going to show you the message frame later. And there is a field in the message called entry type. Entry type describes what kind of message is that. For example, is it find service, offer service, stop service, subscribe to event group, stop subscribe to event group, subscribe event group acknowledgement, or subscribe event group NAC, which is not acknowledged or not accepted. The key fundamental thing is the serialization, very important aspect because you have different kind of machines communicating on service, and these machines might have different kind of architecture, ARM64 versus something else, and how these MCUs or SOCs or machines transform the data for serialization could be different, and it could be understood differently. Same kind of data structure defined, once compiled might mean differently in different machines. That's why the serializers are important. They are described in Autosar, and that helps both the endpoints understand what data has been sent. ARXML is the main mechanism to describe some IP architecture, where you have endpoints described, you have services described, you have events, field, method, everything is described. All the PDUs are defined and described. And as per Autosar Classic, so ARXML file is the key way to exchange the some IP information. Just for again to sum up what service is. The service is a combination of events, methods, and fields. Events can be sent cyclically or on change from provider to subscriber. Provider has a service implementation and subscriber will subscribe to the event. So events are, it's a service is a combination of events, methods, and fields. Methods have operations, so you can describe different kind of operations on the method, and the report procedure call will be sent by the consumer or the client side or the provider side. Then there are fields. There is a notifier to the field which is on change. So you can see difference between events which are cyclically or on change, and notifier is only on change. And there are field getter and field setters which allow you to change, allows the client to change the data on the server. This is the some IP header. So you can see there are different parts of this header. There is a message ID which comes out of combination of service ID and method ID. Then there is a length describing the length of the some IP frame itself. Then there is a request ID, protocol version, interface version, message type. This is the one I described before, like what kind of message type is this. Then the return code and the payload. And you can see how many messages, how many service IDs are possible, and how many. So there, it could be a combination of service ID with method ID or service ID with the event ID. Just to brief on serialization, you have a data structure to be exchanged. Then this is the serialization is described in Autosar, and it describes exactly how a structure has to be serialized to send it on the bus, and how it will be deserialized to understand the content of it by a different machine. Let's talk about service discovery. So it is important aspect of some IP is to locate service instances. Who is providing what service and is it available now? Is the service instance available now? And if a service instance is already running, and then do complete subscription for that service based on pub-sub model. Some IP service discovery only uses UDP. There is no TCP in this case. And some IP itself in the end can use TCP, UDP, or there is also a transport protocol described in some IP over UDP. So there is a choice between using TCP for some IP or using some IP TP over UDP. And there are reasons why they have that. I will not go in those details, but it does make sense to use some IP TP or UDP in many cases. Again, there are a lot more details, but the key thing is, I have this note and think it's probably from the Autosar documentation, but this is the key. Here it's a static, it's a dynamic network, but in case we have fixed IP addresses, we have fixed ports, we know what ECU has what service and what port. So service discovery in case of automotive, as far as I also understand, is it's not the location of the service because it is known, but if whether the service instance is available, that's the key. So service discovery focuses on instance availability and startup and shutdown time more, rather than whether the service is provided by this ECU or that ECU, because when we design the network, we know what IP addresses we are assigning and what port numbers are assigned. So the key thing about service discovery in automotive is not really where the location of the service is, but if the service is available. This is the SD frame. You can see it is based on the some IP frame. You have message ID, length, request ID, and this field basically. And this after this field, if you have service discovery, this message type will describe what kind of service discovery frame that is. Once that happens, then there are something called entries array, and then there are options arrays. These entries array and options array provide additional information to different endpoints of what that service discovery message is. One of the entries could be the IP and port. So when I'm saying I offer a service, I also provide my IP address and port where you can subscribe to that service. So that information is embedded inside arrays and options array, entries array and options array. What I described, for now is what basically service-oriented architecture is, what some IP is, and how it is application layer, how Autosar describes it, what's a service, how you consume the service, how you can request the availability of service, how you can subscribe to the service, and so on and so forth. I want to talk about this framework, which we extensively worked upon, and this uses some of the products which are demoed there. And this allows you to actually profile some IP very well on an Ethernet network, understand the delays or transactions happening between different nodes. What we used in this framework is a NeoVia Pi device. So we use, for example, in this case, we use 3 NeoVia Pi devices. One of them is service provider with an endpoint, and then you have two consumers here, consumer one and consumer two. You can scale it to any number of providers and consumers, but this was the framework we created to understand some IP itself and profile what it takes to actually a node to subscribe and provide the service. We did have to use the media converter in this case, which is RAD1 2, because NeoVia Pi does not have automotive Ethernet. It has 1000-base TX, 100-base TX. So we use RAD1 2 to convert it to 1000-base T1, and we use RAD epsilon in this case. It's a very configurable switch, and you can have all these devices, all these ECUs essentially connected to this switch, and RAD epsilon's one port will connect to PC. This PC, we are running Vehicle Spy software. You have seen the screenshots of the Vehicle Spy today. It also runs Vehicle Spy X. So as one of the presentations we talked about, so before I go there, I want to describe what is inside the NeoVia Pi. There is a Raspberry Pi based architecture. It has a CM4 module, and we have a vSOM IP stack, which is built for Raspbian here, running on this with a configuration done as per vSOM IP. And multiple application examples are created on each of these R5 for their service provision and service consumption. So these units are running vSOM IP, it's running Linux, and it also runs vSpy X. And we did that for the purpose of monitoring local Ethernet interface. So it runs vSpy X, it runs vSOM IP, and it runs for Linux. The cool thing about this is you could remote in from here or using Visual Code, using SSH, remote SSH. This means you can log into each of these devices and control the stack. You can, in fact, remotely build the stack for a new configuration. And so, for example, if you have the JSON file updated for vSOM IP, or you update the application C++ layer, then you can have this configured for any kind of service, any kind of subscription, and any kind of endpoint capability. And similarly, you can route it into this Linux using Visual Code SSH, remote SSH, and same in this case here. That gives you full control of the stack. This gives you remote ability to rebuild the stack rather than connecting to the NeoVia Pis separately on the machine and rebuilding again based on how you want it to use for testing. At the end, you can also have your own ECU connected to this RAD epsilon directly, and it can also transact service-oriented behavior along with this node. And you can use this node to test your some IP implementation in your ECU. So what do you need for this? You basically need a PC which runs Vehicle Spy. I use Vehicle Spy 3 because I have UI made to see what services are being transacted. I'm going to show you a few of the screenshot of the UI. You have vSpy X, which is actually running on these nodes. You also have 4 CAN channels on NeoVia Pi. This means I can do the current project I'm working on is service to signal translation, where I'm trying to study the delay when I translate a the service-based communication into a signal based on CAN. So since this has 4 channels of CAN and D, and I have ETH0 interface on this, running some IP, for example, running Ethernet communication with some IP, I can translate the Ethernet PDUs to CAN-based PDUs and or CAN-based signals and study the delays or latencies what I have. At the same time, for the same architecture, as I said before, you can connect your own ECUs on 100-base T1 or 1000-base T1. And they can, if that ECU has a service providing capability, you can configure these endpoints to consume that service and request service maybe, I don't know, 100 times and, kind of test that way. I do use a software called EACOM. This is our own Windows-based application that allows you to create a some IP ARXML file. And you can create that ARXML file and load that ARXML file either in vSpy X or vSpy 3, and it's going to decode the payload part of the some IP messages. So this is the framework I want to, and to talk about, I want to describe, is what we use to profile some IP and service-oriented architecture. If you have more questions about this or you would like to know more about it, definitely let me know. You do not need media conversion if your ECU has 100 base T1 or 1000 base T1 for that matter, for that purpose. With this framework, I'm going to just quickly show you some of the, example tests we created. Before I go there, I want to talk on NeoVFI and what the role of NeoVFI is. I described to you already that it is running, like for example, the stack we are running, it is at this location. And then it has vSpy-X also with Python interface. This means I can experiment test my some IP right there on each of these nodes. The Ragmon 2 here is just basically a media converter because NeoVFI does not have a 1-body Ethernet. Rad Epsilon is the 10-port managed switch, and since it is so easy to use this switch, I just use this, and I port mirror all the traffic from all the ports 1, 2, 3 from the NeoVFI servers and clients to port 8, and on the port 8 is my PC interface connected for vSpy 3+ analysis. So it's a device which solves all the problems in a single box. One thing I want to mention is in this case, this Ragmon device is actually powered from the NeoVFI, so there is no separate power you need for the media converter. vSpy-X, I described, it runs on the NeoVFI in this case to monitor some IP traffic locally, and basically I also have the Python interface to translate from Ethernet to CAN. Vehicle-Spy, I use this in this framework to monitor some IP, and use EACOM to create ARXML to describe the some IP architecture. I guess with this, I would say there are some examples we ran between, this is a request response example we created, and you can have a UI built to show your service method and different transactions happening. Then we also built examples which are subscribe notify kind of examples, and they show different properties and characteristics of how a field can be changed by a server or a server field change. And then we have examples like how to set and get. So all of these examples you can create, or you can create the code for this. You can write the application on each of these devices, and also use these devices to test your own implementation of some IP. I want to say vSpy-X does have service discovery module completely written by us. It's our own IP. And I would definitely recommend to test your service discovery implementation using vSpy-X running on a NeoVFI or a Linux box. That's another option you guys have. Already with that, I would like to just skip this part, and I would like to conclude this presentation. I'm already out of time. I personally think SOI is the future, because I don't think there is any other way to have that much flexibility in what is needed for the new architectures and new vehicles. I talked about vSpy-X having own some IP service discovery stack. I would definitely try that out if I have to test my own ECU, which has a different stack. And Pi with Rad Epsilon is a great platform to experiment, test, profile your some IP and some IP service discovery. That's all I have for today. Okay, thank you very much.